intense session.
Oh yeah, I'm just a little sore.
Yeah. Need to be twice as fast today because we have only 1 hour and then we need to sacrifice regular meeting time to the joint review.
Do you know any good sources describing the difference between adiabatic and diabatic states?
It shouldn't be too hard to address. Just needs to be fresh and peaceful one.
Oh, I guess these are all one. I know it came up in the review, but like, I don't know, I try to read different sources and like, I try to describe the differences and I always just get confused on the technical aspects.
If you have tuning with non-diagonal elements, where your states before diagonalization do have the physical meaning, like donor and acceptor localized in different spaces, it will be diabatic. If you diagonalize, let's say numerically or analytically, so that upon diagonalization your Hamiltonian doesn't have off-diagonal elements, it will be adiabatic.
That's kind of what I put together.
Yes.
No off diagonal elements, it's diabatic.
Yes. It looks like the reviewer is not very demanding. Just, you're already on the record. It looks like the reviewer is just dragging by his or her knowledge. But there is like long composition of half a page and then just remove the word. How are you? Okay, but how you? The day it looks great. Are you coming for the whole meeting or only for that part?
Whole meeting kind of.
Yeah, keep.
Oh,
Yeah. Just couple more copies. And you, someone will come. So we have about 15 minutes to complete this.
oh, okay. Do you have extra pen?
Yes.
Yeah, I'll give it to Dimitri. I don't know what he's
Oh, thank you.
Let me just leave that in there, see if a reviewer catches.
Yeah, that's
We'll wait until Svetlana and Maxim will come.
oh, yeah, that's right. We need to leave until 5:30. He has the oral English class.
No, we'll wait for Svetlana and then start. So, the next hours there will be joint group meeting between 4 usual groups about the organic complexes. But if you are in the middle of reading, you can decide yourself what is more appropriate for you to either keep reading or participate in the discussion. But if you need to regular when all meetings are finished, next Tuesday we will try to complete discussion sections. So when there were poster presentations in Boston, some of you were trying to make records of the questions from the visitors to the posters. They like to them. If you have organized discussion section, you can just mention approximations in your paper, what were successful and why, what were failures, and then future plans to address it. There is no strict reason to try to arrange records of your very soon, in a few minutes, start of the joint meeting by Professor Sudi. You're going to start soon, right? It's USB or HD? USB on your computer? Or
HDMI program, I think the
adapter for HD.
No, I need to provide you the data, spectrum, quantity, or it's on my list, but it's
Instruction.
Few.
just 3 times.
I didn't know that.
Then we do not have enough class time.
I didn't see the
Try to
figures.
add class of yeah, I think that's important. You know, you can start your work twice a week. You know.
Check if
So how we can switch? Rule it needs some time because it's pretty slow. Not slow as oh. Great. Okay, thanks everybody for coming. Space. So that's the first meeting what we have regarding our project, right? So for those who is not kind of in the topic, so we just won this 4 PIs NSF project, NSF award with this title, where we kind of promising that we will design organometallic complexes with near-infrared emission properties, right? So with desired near-infrared emission properties. So that's kind of pretty big and quite ambitious project, but that's what we kind of want to do, and we want to try in this particular proposal. So these just items during today's meeting, what I wanted to have, like some introduction from my side, and maybe some just short few words from all other co-PIs in this project, right? And some additional questions at the end, which can arise. So just overall information about the organometallic complexes in wind farm. So can talk about a little bit more, but that's the overall objects what we are going to deal with. It's just going to be different metals, right? It's going to be platinum, going to be iridium, and ruthenium. Right? But these are the applications, what they are actually used for, and they're really nice applications of these materials we can get. So all of you are familiar, for example, with the OLED displays, what nowadays we have for the TV sets, right? So that's actually, these materials are one of the important part of the displays, and many other applications like for the catalyst, the sensors, the biosensors, chemosensors, and many other applications. So quite important and useful materials. So the main kind of information about this material. So we have a metal and the ligand around that metal, so different kind of ligands. What the structures actually initially are proposed for that project, which we will start with. Now I'm going to talk about the overall methodology what we are going to apply. First of all, of course, we have to collect the data. So first of all, it's going to be experimental data, what already available and the computational data which we are going to generate. So then everything we are going to collect in one database. So all physical-chemical data, experimental and computationally generated, especially with the quantum chemical methods, what Dr. Dmitry Kilin is the expert in, and his group, of course. And then we're also going to identify structural descriptors, so some kind of parameters which are really responsible for near-infrared properties of these complexes, right? Then the next step is the QSAR modeling. So it's a quantitative, structure, activity, relationship modeling. So this way we will try to put together these kind of structural descriptors what we generated and experimental properties which we got, or try to find the relationship between experimental and computational properties which we generated. So the QSAR is really good for that, and there are several multivariate approaches available for that. And nowadays there are a lot of nonlinear methods for this kind of technique. And the last step, and it's quite important step, is the virtual screening for the best organometallic complex. Right, and this we're going to do like at the last year, at the third year. Now, the database. By the way, I was able to register this website for us at the NDSU, so which calls the materials base. It's not active yet because I have to build the actual website.
And when it's built, and you will assign a home, kind of login information. We need to
So
log in.
yeah, this everything will be provided, but the only thing, they are not allowing to put the database inside of NDSU pages. We can only use them as the first page, for example,
Okay.
where we go. But then there's going to be a link to actual website with the database. So, and I especially did this. So we have actually this domain in nano biodata. So I will try to connect this materials base page on the NDSU with this domain nano biodata. So as soon as you click over there, it will open this page.
So this one is what you are going to create?
Yes, so
or is
right
it-
now it's on the way. So this is
Oh.
already on the way of creating. So we will have something like, you know, this the button over here with the login. So you click, you log in, and then you will be able to enter the all the information to that database. So we will be able to collect all together some experimental data. These actual menu that we have right now, but of course we will kind of change that on the way. I mean, we are going to discuss this question in detail later. So, but the chemical database exists over there. If you click on it, it will open you a table where you can enter data. Okay, now a little bit just quickly all the methods we are going to apply, and actually the importance, the really main importance of this proposal is the combination of methods we are going to use. Right, so it's experiment, it's quantum chemistry, and it's cheminformatics from other side. So these all the in silico methods what kind of available, right? And from one side we are going to use the physics-based methods, so the molecular dynamics and quantum chemical approaches. It's groups of Dr. Dmitry Kilin and Svetlana Kilina. Two groups are going to be involved in that. And from another side, we are going to deal with the QSAR methods and the expert systems. So the database actually built for this kind of thing. So we will create some kind of expert system based on that. And we will use all these combined methods at the end to develop the models and predict the best properties. Hello. Quantum chemistry, just one slide. So that's all different kind of approaches which can be used and the properties calculated. I hope Dmitry and Svetlana are going to talk a little bit what kind of methods they're going to apply for this project. And QSAR, just overall information about the QSAR, how we are going to use all this experimental data in the computation. So we got, for example, the molecular structure of all the organometallic complexes. This the information what we collected in a database. So all organometallic complexes, different kind of properties for them, and as the Y, it's the near infrared properties we are looking for. So we will choose some particular properties which we're going to improve, and then build this kind of set. And the next step is going to be building.
Can you give some examples, like what kind of properties you're talking about?
Everything. So what we are going to, a little bit back. So this page I already registered at the materials base on the website. So the next step, this database, where we're going to collect all the data. It's going to be everything, all experimental data, for example, WM4 has all.
Okay, what kind of data you can provide?
I think it's the UV vis absorption.
All the
molar
absorption,
extinction
right.
coefficients.
Frequencies.
Yeah, wavelength coefficients.
Right.
Therefore, the emission should be the emission energy, maybe
Right.
emission quantum
Lifetime.
yield, lifetime. Yeah. And
Right.
I assume structural information, you either if there is a crystal structure,
you-
bound length, bound angle, and if not, there should be from the simulation optimized geometry.
Right, but we need
you
some
have
crystal
this
data as well.
in different solvents, for example, right?
The crystal data cannot.
No. I mean the absorption spectrum.
Yeah, we have those.
Like if it's different solvents, you also collect all that, or what?
Right. So and some solubility, if there is some solubility data, if they are
We
soluble.
usually do not collect the solubility.
You don't have?
Yeah.
Do you have some melting points data?
No.
No.
No, we just
What
know
kind
the
of
organometallic.
what kind of other physical chemical properties you measure usually?
I do not think those are important for the optical properties.
It's not important, but it's better to collect everything what you have.
Transition metal, I mean, organometallic complexes, the melting point typically is pretty high. It decomposes before it.
Oh, it's decomposed before,
Yeah,
so okay.
higher than 200 or even 250 or even 200 degrees Celsius. So I actually do not think those are relevant to.
Just as example, I mean, you probably anyway measure some other physical chemical properties in addition to absorption. What else you look at the
NMR. Okay.
NMR, right?
Yes.
NMR shifts
Photon NMR.
and
mass
coupling constant.
spectrometry.
Right.
Yes, that's right. Coupling constant. If we are.
That's
able
also
to-
important because
Oh,
this
okay.
way
Those are
we
the
will relate to
structural.
the structure
I see.
somehow. The
Coupling constants?
Coupling constant
Yeah.
means the
From
photon
NMR.
Yeah.
NMR. That's also important because coupling constants tell us about the angles which you have in the real
The interaction. Yeah, that's right.
in the solution or like in the real world between the bonds or between some particular fragments. So that's important because simulation not always can give us some kind of really unique angle for some particular fragments, right?
And what about isomers? Like how you collect this information? Because it might be exactly the same chemical compound with different conformational configuration.
I think for the complexes we are working with, they typically just, even there are, in principle, there are a variety of stereoisomers are possible, but actually what you get under that experimental condition, you only get one isomer.
Well, previously we did something. You remember, like there was a paper where we
No, it
Computationally-
was, I think it was Brandon did it wrong. It's not due to the presence of the
No, we found out that there
isomers.
were some isomers, some percentage of isomerization.
No, that was not the case. I think he did something wrong. So and the,
So computationally, you can generate any number of isomers if you can, and put it to database. But at the end, the QSAR model actually will be able to choose the right one, which really well correlates with the activity of this desired property. We can do that still. We can put like, I'll show later the table, and then we can discuss it looking at the table, this kind of question. So as soon as we got the model, we can use that model to predict the properties and activity for.
And again, you always need to have it like this figure with linear minus
Yeah,
linear.
it
You have
means it.
some property one on a one
It means
axis
the
and
well-
property two on the other axis, right?
Yeah, not some property. This is the experimental and this is the calculated properties. They always should be as close as possible to each other. The experimental, that's the graph of correlation between experimental properties and the calculated ones. So then if they are close to each other, they all will be on this
This
line.
is an issue. Well, because we're not really providing the spectra with
I will
exactly
provide.
same
No.
precision.
You guys will provide the physical-chemical data. And I will provide.
But our
the
spectra usually can
calculate-
be blue shifted or red shifted with experiment. It's very rare when our spectra is just like, you put two spectra together and they can sign 100%.
Right, I understand, but it's
Then
not
would
necessary.
it generate some
I'm
problems?
gonna look
for-
at your spectra. It's not necessary.
But then what do you mean theory versus experiment?
I think you just need to have a good correlation or systematic error if we see it. Everything you calculated for one
You know,
series
in
will-
my model, I can include several parameters, not just
Oh,
the spectra.
when you say
you-
theory, it's already from.
It's already model, QSAR model, not just your calculated data. So it's a model which has several parameters inside. One from the spectra calculated, one from some other structural data we calculated using our methods. So altogether, which gives us a good prediction. But we're still going to discuss it. So this is as example, the descriptors which we are going, I can generate using the QSAR methods in addition to what you can calculate. So just looking at the chemical structure of the organometallic complexes, we can generate about 4,000 or 5,000 different kind of descriptors. They are like all structure related descriptors, different kind of numbers which related to the structure. Easily we can generate
And this
5,000
is
per
you get
structure.
it in kind of mathematically. The only thing which you need is the structure, the
Right.
geometry.
The only thing what I need is a structure to be able to calculate 5,000 different properties per one structure. And then I will choose the one which more or less well correlates with the desired property,
With the physical property.
with the physical experimental property. And it can be like several parameters. One parameter can come from the quantum chemical calculations, one parameter can come from our additive formulas, let's say. And this is like iterative process. It's the special algorithm which calls the genetic algorithm selects the best ones. So then there can be the geometrical and 3D shape descriptors, which, for example, coupling constants from NMR or calculated NMR. Yes?
So you say theory, and I know that DFT highly depends on the functional.
Right.
are you
You
going
repeat my
to
question actually.
select a functional and say this entire database is PBE1 PBE? Or are you going to select whatever functional was in the paper?
No, but guys, you have to choose. I mean, which function works really well for you to predict the experimental spectrum.
Okay, so this
Really close
has
to
to
the
be one
experimental.
functional.
Right. It's
Okay.
better to have just one function which works really good for these particular kind of systems.
But again, if we have different approaches for different DFT methods,
Right.
But why you have to use
molecules.
the different DFT methods? You
Huh?
choose only one. Of course, you.
because some of them work better for one type of metals, another for another type of metals. One work better for those ligands, another for those ligands.
Then we will build QSAR models for that particular metals.
And even for the, what did they talk about is for different series, we usually, synthesize different series of complexes with some structure are the same, some parameters.
The basic,
Yeah.
the core is the same, and then just
Right,
side
maybe
groups
some
are changing.
stations are different, or the degree of pi conjugation are different, or maybe we just, do the variations on the diimine ligand, some, series we do the diimine ligand, the changes on the CN ligand. So for different series, their theoretical, calculation, the functional code change, PBE1, PBE, probably that one is the most frequently
Right.
used.
I understand what
It's
you're talking
really,
about.
yeah.
But from another side, I think there should be some balance. You cannot just
No,
use
we
all
already see-
100 different.
No.
For
It's
example,
just maybe
for
I think
ruthenium, we already see that functional
Right.
should be not the same as
That's
for
what you can do.
ruthenium.
You can choose one good method for one metal. So, for example, for ruthenium, you use one particular method, for platinum another, and for we have the third one is
ruthenium, platinum, iridium.
iridium. You can choose third one, and then it's still gonna be okay. We will just have three different models,
But even
For-
inside this, going from one series to another, we see
but then
some
it makes
fluctuations with
everything
some,
complicated. We still can discuss it and see how we can implement, but it makes everything complicated. If you use different methods for different compounds, that's kind of not.
I think PBE1 or the B3 leap are the two, especially PBE1 is the most frequently used and works, works the best for most of them.
right. But
Yeah.
we still have some.
Yeah,
You
we
know,
have
where we
some, a
increase in this
few,
portion
yeah,
to-
with B3 leap, I think it's commonly used,
If we
just three.
select three
Yeah.
basic ones, then it will be still good with the methodology.
Mhm.
So no problem.
Yeah, I do not
Okay.
think we used, yeah.
We were
And there can be some hybrid descriptors as
Where
well.
is a percentage in BB1 for several
Okay.
complexes to be in a better unit? And
What?
it was really like 38, or I don't remember,
But-
32 or something like this instead of 25.
Wasn't changing the hydrofact to shift it to qualitatively and quantitatively match? So if it's shifted systematically, I thought that was fine.
Yeah, that's right, that's what I think, if it's a systematic variation, probably it's okay.
It depends what you call by systematic.
Everything, every series is, they are all blue shifted,
We
all
already
red
know
shifted.
It's actually shifts differently your pi-pi transitions versus MLCT transitions,
Yes.
right? So,
So
kind of
the-
not
for
exactly
QSAR
systematic
purposes,
for one band, but not for the other.
Oh, no, what
For
I mean
user purposes.
systematic is for that series of complex, all of the charge transfer band, for example, blue shifted, the pi star band, or red shifted, that works for each of the complex in that series. So that's a systematic error. I'm not really, go down to the charge transfer band versus the pi star band. I think what we try to build up the correlation is when structural varies, how that impacts the protein, as far as it's a systematic way for that whole series.
if there is a systematic error, so it's okay, we can also deal with that.
Well, again, it's not affecting very much the geometry, but it's much more sensitive to the spectrum.
Okay. So we'll see. Let's discuss it in detail separately. Okay. So of course, there's some problems with the QSAR as well. So I see there are problems with the quantum chemistry to choose the right method, but with QSAR we also have some kind of problems which we have to deal with and select. For example, QSAR mainly developed for the small regular organic compounds, which are like different kind of pharmaceutical compounds. Most of them are small organic compounds, and organometallic complexes are quite large and having a metal inside, which makes everything more complicated. So we have to somehow find a solution for that. Then, of course, there are limited experimental data for the organometallic complexes. If you take a look at small organic compounds properties, you can find databases with millions of compounds and physical data for them, physical chemical data, experimental data for them. But for organometallic complexes, I think it's really limited. And the third one, the descriptors, so these theoretical descriptors which we are going to generate, actually also mainly developed for the small organic compounds. So it's going to be difficult to calculate them for metal organic complexes. But still, I have some idea how to deal with that. And hopefully, we will be able to overcome that problem. So that's how, for example, looks like the classical QSAR, where we have regular organic compound and generated descriptors for them, right? It's like two-dimensional problem. So this is the list of chemicals, and it's the different kind of properties we generated for them. But in case of metal organic complexes, we got this third dimension, the different metals. So we can have similar ligands, similar chemicals, but different metals, which also makes it more complicated. The problem in the QSAR for that, building the model. These just as the examples what we I use, for example, in our studies, some kind of atomic orbitals information to use them as a descriptors for nanomaterials, but we can do the same for the metal complexes, right? We just use the atomic, the orbital, the connections, let's say, between the orbitals as the some walk counts. So this is just as the from the graph theory, just as some kind of information descriptors, let's say. That's what the Isaev, the Alex Isaev suggested to use the density of states as the fingerprints for different kind of materials. So this we also can use somehow, since every organometallic complex will have different density of states picture, right? That's the overall strategy what we're gonna use. So organometallic complexes, the modeling from one side, experiment, then building the QSAR model, and then the predicting activity for the untested one. So that's kind of standard procedure. We'll be trying to put both experimental and computational data. Okay. This comes from different slide. Okay, so this is the same what on the previous slide. The only thing that's what I call the virtual screening. So when we build a model based on the experimental data and the quantum chemical and generated descriptors, right? Then based on that, the next step is going to be to synthesize virtually a bunch of metal organic complexes, like thousands of them, hypothetical ones with different ligands which you never synthesized, for example. Right? So these white points, for example, a lot of metal organic complexes which not synthesized, and the black is what we have experimentally. But then, based on that, the QSAR model will be able to show us which one among these white points showing the best activity or property we are looking for. So for example, this one. And then based on that, we will be able to suggest which one is good to synthesize. So that's kind of the way we can work. And this how the database may look like, right? So some index per compound, so the metal organic complex. So this is the information about the chemical structure, let's say. So it can be some smiles, if you're familiar with the smiles notations, how to represent the chemical structure using the one stream line. And then, as you can see, the one compound will be split to 3 or 4, it depends on how many different parts of the molecule we have. For example, if you have one metal and one ligand, one type of ligand, you will have like splitting to 2, just what kind of metal, and then the ligand. If we have 2 different ligands connected, so we will have like one more option. And then there are going to be properties for the metal itself, for the ligand, because I can collect different properties just for the ligand, which is also important. So, because ligand actually quite often also define what the final property going to be, right? Since by replacing the ligand, you replacing the final property, desired property you're looking for. So that's for us, for the cheminformatics, this is also quite important to have just initial different kind of property for the ligand. And then properties, different kind of properties for the whole metal organic complex. So this kind of structure I'm suggesting to have for the database. That's the overall steps what we can use, like generating different kind of descriptors. Descriptors I call anything what we can measure experimentally, quantum chemically, or can generate using the cheminformatics method, different kind of descriptors. Then the modeling, trying to find some properties, building some kind of correlations, and then find the best material we want. And this is from our proposal, how we are going to interact. So from one side, it's going to be synthesis and the public data on experimental properties, the computational chemistry data, of course, the quantum chemistry mainly for here, then the cheminformatics, then virtual screening, and again, the suggestion what to try to synthesize, and then we can do these kind of loops 2-3 times before we get really well-working candidate for us. So that was the main idea, right, when we were writing the proposal, to make this loop. Okay, and these are steps. What also we had the proposal, so these actually the same steps what I was just showing at the picture. So extraction of the experimental computational data from public sources, data generation, so different kind of quantum chemical cheminformatics calculations, also generation, getting new experimental data, then the data mining, and the QSAR studies, virtual screening, And validation of the results. And as you can see there, the marked columns, it's the first year, second year, and the third year. So that's what we have splitting. So questions?
I'm just wondering, I provided you with our publication list. Was that good enough for you to start with?
Yes.
Abstract?
I look at them already, so it's good enough. So I can probably try to take some information from that. First of all, structures and different kind of data from absorption spectra you put over there and put it to database. So I will start and kind of show what we can extract and put there. Yes, Jared?
Which algorithm you are going to use in QSPR method?
Which algorithm? Oh, there are several of them. Of course, we will start with the simplest one and more transparent one. We call transparent because it's easy to understand the connection between the structure and properties. So it's a multiple linear regression. So just linear regression methods. But then, if these linear regression methods not gonna work for us good, we're gonna switch to non-linear methods. So it's gonna be partial least square PLS methods, and then to more sophisticated ones like supporting vector machines, the neural networks, and so on. So different kind of algorithms that we can easily use. That's not a problem nowadays. I don't know, are we gonna go to deep learning algorithms, but probably no. It's method where you don't know what's going on inside. I mean, what kind of connections between the properties and the structure you get, but you get just answer. Is that good or not?
Is it
Like
a
more.
problem with machine learning that we don't have enough data?
Say it again?
I mean, not machine learning, neural networks, because you need like as many data points as you have parameters.
Right, because neural network methods need a lot of data to get learned well.
Yeah.
So it depends on us. In our case, I don't think we will have a lot of data.
Oh.
Like for neural network, it should be like thousands, to get really good model, and more, like hundreds of thousands. But we will have maybe hundreds points, and that's it, no more. At least at the beginning. But based on this 100 point, I can generate thousands of hypothetical ones and choose from them one which gonna be more or less good for us. That's kind of the idea.
When you say point, it means like each compound,
Yeah, each structure.
each molecule. Okay.
Each, it's point, I mean, in a database. But yeah, each structure. Okay, so anyone else wanna step out and tell something? What kind of other ideas or approaches can be used? Oh, we discussed everything.
Pretty much. I'm just wondering also, since the project, when we wrote the proposal, it included the near infrared emission and also the nonlinear absorption. Nonlinear absorption involves the ground state absorption and excited state absorption. We certainly will always do the transient absorption that's related to excited state absorption. I think Smelana tried to also calculate it, but so far we do not have any data for the excited state absorption. I mean, just
So-
based on the experimental data, whether that's still good enough to proceed.
Just with experimental data?
Yeah.
Yeah, we can start with
Transient
just
absorption.
experimental data, because I can generate some additive descriptors, let's say, not
Right.
quantum chemical descriptors, just looking at it.
Yeah,
as
pretty
well.
much in each of the paper, I sent to you from our side of the work, we have both the ground state absorption and transient absorption,
Let's say.
emission, spectrum, quantum yield, lifetime. All those are available in the from in the paper. The only thing is we do not have lots of crystal structure data. We're just unable to go through crystal. So
But you can use computational
Yes.
line geometries for this plane.
Yeah, that's what we forced to do. I mean, of course, it's always
Like,
good to
you
have
kind
the
of a
more.
mixture. You will take geometries from calculations and use then experimental data on properties, right?
I remember.
But yes, we will have both of them.
Yeah.
No, I mean like those where we're missing quantum chemistry calculations, you still can use the geometrical parameters,
From crystal.
descriptors based on theory, but connect them to the physical properties,
Right.
optical properties from experiment.
From
it's not a
experiment.
problem.
So
Yes, I
at
can do that.
ECS, I was talking to a guy from Gaussian, and if we use an approximation, we can get absorption to excited state cross sections. And I ran, so it's a Tom Donkoff? No. T-A-M-N Donkoff? So,
Well,
using
the
a-
problem with your calculations of the excited state absorption was that we are in the wrong range of spectra
yes,
because
but I think.
because the lowest transition, right, lay in the red, actually infrared range, right, and this is what you not even measure.
But I
We cannot get to the visible range
think
because of the too many low
that
energy
this
transitions.
approximation might be able to compute more states than what we had with whatever the guy was from Florida. I think it might be able to check, like, look into a different methodology to do the excited state to excited state absorption.
Actually, University, etc.
Yeah, that
this is
kind
what we did. But
But-
there was nothing, it just was based on the linear, actually, calculating non-linear terms,
Yes,
the absorption, right, that's it.
but there might be a way to do it in Gaussian 16.
I cannot believe that you can avoid the same problem.
Yes, there
Whatever
might be
your
a problem.
approximation, it's not dealing with approximation, it's dealing with a number of transitions which you can get, right? And just regular TDDFT will not allow you to calculate spectra which will be consist of millions of transitions. It's just impossible,
Yeah.
right?
I'm not arguing that, I'm saying that
Your matrix is becoming too
there
large for
might
this.
be a way to do it, and we'll have to look into it.
Okay. So in overall, everything understandable. So the first step for us left to just create the web page, right, where you will be able to put some data, what you have.
And do you have already some ideas on the format?
Yeah, that's what I was talking about.
Please.
No, that's still not visible. So, okay, once again. So that's the metal organic complex we are talking about, right? Just name. This is the structure. We can put any kind of structure format over here. So right now it's smiles over here. So we have to have some kind of structure file. We can upload the file over here instead of this sort of coordination.
So for
Yes.
you, it doesn't matter which format of file we
Doesn't
prevent?
I can convert easily within
Seconds.
Because
second,
all our data
less
are
than
in
a
the
second,
input of Gaussian, right?
between the hundreds of different formats. I can easily.
The
convert.
format of the input,
No.
the input format
No,
of Gaussian.
I will make easy for you. So you just upload whatever you have, but it should be some coordination file, some coordinates.
Don't
Doesn't
you
matter what kind
have
of content.
connectivity for a smile string?
Hmm?
I thought you had to have connectivity. So if it's a double bond or a single bond. Because
It
if,
doesn't matter actually. So the program, based on the distance between the atoms, can also approximately understand if they're going to be double. Or we have to decide. You really want to show or there double bond between atoms or the single bond, explicitly or not. Or just like in a Gaussian coordination file, it's like automatically the program will select. It doesn't matter actually. For many kind of descriptors, what we're going to generate, it doesn't matter. There, it explicitly says there is a double bond between atoms or no.
So then, if we're in the loop, and you give us a smile string, how would we convert it into an XYZ and then saturate all the carbons, and then a sp2 carbon, we would put 2 because there's not double bonds?
No, he's saying that
But you will convert
his
both ways.
descriptors will be built already with the idea
I understand that.
that it would be already including this information.
In
inside.
Gaussian, are you using this information? You don't use all this information.
But
you
we
have
don't
double
convert
bond or not.
smiles to XYZ.
Yes, you can easily generate XYZ from smiles, because that thing actually keeps inside all the information between these.
Okay, I guess whenever I've done it with
Never
RDKit,
done. Yes.
you have to have connectivity, and if you don't and you say saturate the carbons,
It's coded here, the connectivity actually, it's coded.
okay.
Yeah. There's some information there about the double bonds or the loops. So if it's in brackets, it says it's separate cycle. So, yeah. So just information about the molecule, and then we have to put what kind of metal is there or what kind of ligand is there. Okay, and then you guys, if you
I mean,
calculate
again, kind means just name. Or what you mean kind? Like
there
we just
will be
make our
name,
annotations.
there will be a name and there will be structure. So there will be structure. No problem. So quite often this structure can be really extracted easily from here, because over here we have only, the one metal. If we remove it, actually all the rest is the ligand information, right? Ligand structure.
But
Of
then we
course
also need to probably split it into 3 parts. Metal ligands, which are coordinated with metal, right? And then the side groups, substituting groups.
Yes, that's also
Actually,
we can.
that's actually how we call Syria, right? So series is different just by substituting
There's
groups.
ligand and several substitutions, right? To that ligand.
But the core part of ligand coordination and metal stays exactly the same.
Okay, so then this part will be split to several of them. So we will see. We have to still discuss the final structure of that database, which will be easy to understand for all of us, not just for me. Well, and then you put all the properties like from experiment or from the quantum chemical calculations for that. These, for example, columns for property of the whole metal organic complex. But over here we have splitting, as you can see. So over here we can put the properties which I can generate, for example, for each component of that metal organic complex.
And then you say properties is the same as descriptors. So
Yeah, the same as descriptor. Properties, descriptor, that's the same thing. Because in QSAR we quite often.
But
call
then,
this-
am I right? You kind of, again, we can split it into the descriptors generated based on experiment, descriptors generated based on theory.
Right. It will be kind of separate, but still, for one metal organic complex, we will have it in one line, in one row, everything. But we have, names for these columns, so we will name them, and you will easily see which one are experimental, which one are calculation. So that's kind of structure proposed.
Yeah, am I understanding this correctly? The descriptors are the structural related parameters.
Right.
Properties are those optical properties we are interested in. Ground state
Physical chemical
absorption,
properties.
yes,
Right.
okay. excited state of absorption, emission, quantum yield. Those supposed to be the properties. Those are not the descriptor. Descriptors, bound length, bound angle, maybe crystal field, splitting energy, and what else? Coupling constant. You just mentioned.
Right, yes, we call them like desired properties, so the properties what we are looking for, I mean, we want
How that
improve.
related to the structure. For example, maybe this particular bound length is really important.
Really important,
Yeah.
right.
Then longer it would be better under the trend. Then we should try to make it
Great.
long. Yeah.
So among these 5,000 descriptors, there are some descriptors which only describe the bond length between some particular atoms,
Yeah.
between two atoms. So if that bond length really important, it will pop up right away for us when we will do the QSAR. If it's really well correlates with the optical properties here, it will pop up.
So basically, your system or what you are doing, the chemoinformatics is you, for example, you just mentioned 5,000 descriptors, and then you try to correlate each of the
Each of them.
to the properties to
To the
see
property of
which
interest.
descriptor or descriptors would correlate with the
Right.
property much better.
Right.
Those
So
are
there are
kind of-
several.
What if we have one it's a one or two descriptors correlation, then it's clear what to do. But what if you have from 5,000, I don't know, 1,000, which really
Not
correlates to the
1,000,
same
but
properties?
it can be like 10 or 15 or 20 of them. Yes, but not 1,000.
So you do line in
So it's really
multi-dimensional
narrowing
space.
down,
Right, it's line in multidimensional space. Yeah.
Right.
but you at least expect that it will be narrowing down to a few rather than hundreds.
Right, yeah. Because, you know, we will always try to validate our model. And validation, it means we will check that model on the separate set, which wasn't involved in training that model. So it's a separate set. We right away put aside some set, and then as soon as we build the model, we will check the prediction for that separate set, for which we have experimental data. And then we will compare what the model predicted and this experimental data. If it's good, the model works. If it's not good, sorry, we will have to choose another model.
And by another model means like you're switching
We
between
will do the
algorithms.
simulation again, I mean,
What?
all these iterations again until we select different descriptors. So
Ah.
that's another model. The different descriptors and check it. So right now I'm doing this kind of thing with my students. So by the way, I have 3 students, Anna, Queenie, and me. Yeah. So they are working with the polymeric materials, of course, but
Anas. Anna, sorry. I saw that.
yeah, Anna, yeah. You say Anas or Anas?
Anas.
Anas. I'm always wrongly call him Anas. So Queenie and Nate.
Sorry, I did not get your name.
Need.
Me?
Yeah, it's like the notebook. I don't know if you have one.
Oh, okay, I see.
So right now they are on a way of learning these the steps what we have to do to build a model. So they are.
So
That's why I can ask them to
Are they
come.
all involved with this project? or
No, right now no, because 2 of them on CPM program, so they have to deal with the polymeric materials, and one of them, Queenie, on biomedical engineering. But still, for the biomedical engineering, we use kind of some polymeric materials for biomedical applications. But probably in part, each of them will be involved in that. So we'll see. Because first of all, over here is most important the methodology. So for them, it's quite important to learn that methodology. So at some particular steps, each of them will be involved. And then we will see how it goes. Okay.
So you
Or
said
set-
you already did some of the interim abstract some parameter from our paper and put it in the database. Are you doing that or somebody? Who is
No, I will ask the students, and also I'm expecting a couple of visiting postdocs, let's say.
Oh, okay.
Yeah, one of them gonna be completely involved in that.
I'm also
For a few
wondering
months.
the timeline. A few months, you talk about 3 to 6 months, or how soon?
3 to 6 months.
Yeah, I'm just wondering, for example, how long, I mean, for the timeline to generate first the database set and then try to,
Ah. We will try to stick with this plan what we have. So within first year we need to collect as many as possible data within first year, but probably the initial set which will be available, which I will be able to extract from the papers, like within 3 months. Within 3
Okay.
months, some kind of. How many, for example, you sent me about 30 or 40 papers.
no, I sent you 60.
60,
60
yeah.
or 70 papers.
So how many different compounds you think? Because I wasn't trying to even count in these 60
There
papers.
should be 60 papers, it should be at least 300.
300
Yeah.
different compounds, different organometallic
Yeah,
complexes.
different.
So I think about 50 can be collected from these papers within 2-3 months, and then we can.
What I'm
them.
considering is meanwhile, we need to do is because the first half year has been more realistic. Probably we will not be able to get any feedback from your side. So we probably just based on our experience.
Yeah.
We
You're still
synthesize.
generating experimental data. You're
Oh,
still
okay.
synthesizing and measuring the properties. So you still it calls the generating data.
Okay.
First year you're working just based on what you
What
have.
our experience,
Right.
empirical, yeah.
Right. And on the second year, we start to get some kind of models where I have this. It was at the end.
Your call will be disconnected.
So that's what we have. So the first, it was the second year and the third year. Anyway, we discussed the main stuff.
Yep.
Okay, thank you.
I can bring the slides back.
No, come on, we already discussed whatever we want. You can override that lady, right? You can override that lady.
So we are going to meet next month again, or?
Next month, right? But we have to find some different time, or at least shift it to 4 p.m.
But you also planning to do some synthetic work on
Right. The wind farm
that's
still
what I guess.
continuing.
We will continue, based
synthesize.
on our experimental
That's
past
what-
experience, we try to keep working.
Right.
on
At least first year.
some data.
At least first year, you still synthesize and generate the data just based on your intuition.
Yes.
That's what we kind of described in the proposal. But since only at the second year, she start to get some feedback from us what to
Then we will have
what
some
to
direction.
synthesize. Because I'm pretty sure it will take for us at least 1 year to figure
Feel
out
that, yeah,
how we can, put that methodology to work. It's gonna be complicated.
yeah. I want to know the big picture, how exactly. Yeah.
Okay, so thank you. So I will send the slides. If you want, I can send slides, but I wanted to see the invitation for the second meeting
Oh, okay.
in few days. We have to find, maybe Doodle to decide what day is good for us.
I think October 30th, right?
Yeah, we put some approximately at October 30th. You say that's good for you, 4 p.m. October 30th.
We already did that.
We discussed at least.
Oh, okay. I think that should be fine because now it's supposed to be October we have 31st, right? Yeah.
Yeah.
Thank you,
actually,
guys,
it probably will not
for
work.
coming.
We have a deadline for proposals.
Yeah.
Yeah, Bhakti, it will not work. We have a deadline for proposals.
But
On 30th?
I assume on
But
30th
before
we
30th,
should
you
be
have to
able
do everything.
We do everything last minute.
Last minute.
I do everything on last minute.
Not me. I need
Yeah.
to be.
But anyway, it's
I mean,
gonna
I
be.
can try, but I would really.
It's gonna be
not
submitted
plan
before
anything
4
for
p.m. So,
So you imagine that I submitting proposals and come to talk with you?
yes, you have to be happy, you know, this time.
31st is then which
It's
day
Wednesday.
It's Wednesday.
Oh.
That should work. Yeah, 31st, 4 p.m. should be right.
Going back
Yeah.